All right, you crazy kids, here's your lecture on limiting reactants and percent yield. This is going to build on our previous lecture on stoichiometry. Okay, so to start off, we're going to build a bicycle. So if we build a bicycle and we have these pieces, you might be able to actually write a reaction for this type of bicycle build. It looks like you would need one frame plus two wheels plus one handlebar, and that would produce one bike. All right, so it looks like I have a 1 to 2 to 1 ratio. These are the pieces of the puzzle that are required. And I can prove it to you, I guess. We could, show you that this will actually build a bicycle, so we're not, lying. It's a pretty good-looking bicycle. It doesn't have a pedal. Maybe it's a Strider bike for a kid. I don't know. Okay, now, if I am a businessman and I have a giant warehouse full of all these things, I'm not going to have, the perfect number of things to make a bicycle. All right? Chances are I'm going to have, odd numbers of them, depending upon how much they cost and where I could buy them and what was left over previously, so on and so forth. If these are my numbers of how many things I have, could you figure out how many bikes I could make? So glancing at it, I could probably figure out, I think this is what's going to limit my production, or what's going to halt my production. I think it's going to be the handlebars. Because it's a 1 to 2 to 1 ratio, if I take my wheels and I divide by 2, I would have 2,407. So it's clear to see that the lowest value is going to be the thing that really controls your reaction. In chemistry, we call that the limiting reagent or reactant, or the LR for short. The components that are left over, we call these the things that are in excess. All right. And we can figure out how many are left over by some simple subtraction, right? You have how many you have in excess, you subtract your limiting, and that'll give you what's left over. In this case, we have 152 wheels left over. All right, so wheels would be 152. And for my bike frames, I get, I think, 28. All right, now, if you can follow that because you're very familiar with bicycles, or you've seen a bicycle at least before, this lecture on limiting reaction stoichiometry shouldn't be that bad. All right, the whole idea is to identify the thing that's going to control your production, and to use that thing that's going to control your production to predict how much product you're actually going to have. That's the whole idea. So some definitions for you. Your limiting reactant, the reactant that limits the amount of the other reactants can react, or simply stated, the reactant that runs out first. And then you have your excess reactant, substances that are not completely used up in the reaction. We're going to give you an actual reaction here to kind of go from and see how that looks, and hopefully this will make sense. I've also come up with a step-by-step process to help you identify what's going to actually limit your reaction. It's not going to be as easy as this, because this was like a 1 to 2 to 1 to 1 ratio, and quite frankly, life isn't always that easy. But we will try our best to explain it to you in a simple fashion. So, first thing we're going to do is write a chemical reaction. Notice how it's missing from this location, and our previous lecture was all about starting with a balanced chemical reaction. Same thing, any stoichiometry problem, that's what you need to start with. So we're going to have our HF plus our SiO2. And I don't know if you guys would be able to predict these products or not, but it's fine if you can't. We would have SiF4 and, I don't know, some H2O. All right, so that's the stuff. Notice how it's not balanced, so we do need to balance it. We'll put a 4 here, a 2 here, and now we have a balanced chemical equation. All right, now, the step-by-step process to identify the limiting reactant. Okay, we have 2 moles of hydrogen fluoride, 4 moles of silicon dioxide, and we're figuring out which one's going to limit my reaction. Easiest way to do it, in my mind, is to choose either reactant. So randomly, I'm just going to choose HF. Right, that's the thing we're going to start with. We're going to calculate the amount of the other reactant that's required. So I'm going to start with what's given to me in the problem. My 2 moles of hydrofluoric acid, or just called hydrogen fluoride. So 2.00 moles HF. I need to calculate how many moles of my other reactant are required to react when those 2 moles react. So I'm going to work towards silicon dioxide, meaning moles of HF are on bottom, moles of SiO2 up on top. And then we look to our balanced equation to figure out, what values go here and here. It looks like we have a 4 and a 1. That's going to give me an answer of 0.5. What does that mean? Well, that means when 2 moles of HF react, I need 0.5 moles of SiO2 to react with it. That's how they mix together. That's, in a perfect world, if I were putting those two things in a beaker, I would get all product, have nothing left over. But chemistry is never like that. In chemistry, you always are going to have something that limits and something in excess. It's just how the world works. I can explain that more in detail later if you're truly curious. If not, you can just take my word for it. All right, so now we're going to be comparing the calculated amount with the actual amount provided in the problem. So the actual amount provided in the problem is right here. I have 4.5 moles of silicon dioxide. Our last step says use your brain. So this says when 2 moles of HF react, I need 0.5 moles of silicon dioxide, SiO2. Do I have 0.5 moles? Well, sure. I got 4.5 moles. That means I'm going to have a whole bunch left over. In fact, I could do some math and calculate. I'm going to have 4.0 moles of SiO2 in excess. Not all of it's going to react, which identifies HF as your limiting reactant. That's how that works. Now, just because I said it was possible to do either way, and this even says choose either reactant, we're going to show you what this looks like if we calculate it with the other reactant. I'm going to make that nice and small and put it up there so we can have access to it later. But let's pretend like we picked SiO2 as the thing we're going to start with. Oh, I didn't want to do that. Here we go. That's better. All right. So we're going to take our 4.5 moles of silicon dioxide, so 4.5 moles SiO2, and we're now comparing that to moles of HF. So moles SiO2 are on bottom, moles of HF up on top. That's a 4, that's a 1, that gives me 18. We'll write it in a different color so it stands out. Moles of HF. We're comparing the calculated amount with the amount given to us in the problem. We were given 2 moles. Now we got to use the brain a little bit. So when 4.5 moles of SiO2 react, I need 18 moles of HF. Do I have 18 moles of HF? No, I only have 2. That means there's no way all of this is going to react. This is going to be in excess. Because I have less than what's required, HF is going to be your limiting reactant. So either way, when you do the calculation, it's a different thing to think about, but you can still identify the limiting reactant. That's how that works. Let's see what else we can do. In a bigger problem, we're not going to be just given moles and moles, and in lab, we're never really going to be dealing with moles. We're more likely going to be given grams. So now we have a different calculation. It's very similar. We're still identifying the limiting reactant, but now we're given grams and grams. So a little bit more work. We still need to start with a balanced chemical reaction. So we have 167 grams of iron react with 35 grams of water to produce iron 3 oxide and hydrogen gas. Yours might say water there because that was a typo, but I fixed it. I don't think I fixed it on your copy. Sorry. Let's write a reaction. We have iron and water to produce iron 3 oxide and hydrogen gas. All right. We need to balance this beast. Oh, what do I need? I need a 2, I need a 3, and a 3. Now we're balanced. I will put states of matter here. Why not? We have solid, we have liquid, we have aqueous, and we have gases. Cool. I don't know if I did that up top. No, I didn't. This is going to be an AQ. Silicon dioxide. Ooh, that's going to be a solid. And silicon difluoride. That's going to be a solid and a liquid. You don't need to know that right now. Okay. So what is the limiting reactant? So we pick either one, and we're going to work towards the other reactant. So last time I started with the first component. This time I'm going to start with the second component. Why not? It doesn't make a difference. You're still going to be able to identify the limiting reactant. So I take what's given to me in the problem, my 35 grams of water. And I need to calculate now the unknown grams of iron that will react with it. Oh boy, I drew 3 lines because I first have to convert my grams of water. That's a 2. That's a terrible 2. Let's try again. To moles of water. Then I can convert my moles of water to moles of iron. And finally convert my moles of iron to grams of iron. This middle section here, that's stoichiometry, right? That's the heart of stoic, converting moles of one thing to moles of a different thing. But considering the problem's giving us grams and is asking for grams, I can't just like go right to moles. I first have to make that conversion from grams to moles. Okay, so let's backtrack. We need to do a little math here, right? What we're doing is we're comparing our water value to our iron value. All right, that's our first calculation that we're going to do. So I need to figure out my molar masses of water. So we're going to have hydrogen times 2 is 2.02. We got an oxygen, that's 16.00. We add those up, we get 18.02 grams per mole. That's 1 mole is 18.02 grams. Awesome. Our next component, we have a molar ratio. The molar ratio comes from my balanced chemical equation. We're going to have a 2, we're going to have a 3. Our last part comes from the periodic table once again. On the periodic table, 1 mole of iron happens to be 58.55 grams. When I put this on my calculator, and you guys should try this to make sure you're able to complete this calculator action, it's 35 divided by 18.02 times 2 divided by 3 times 58.55. Let me go ahead and put that in my calculator too. So we have 35 divided by 18.02. Oh boy, made a mistake. 35 divided by 18.02. All right. We got times 2 divided by 3 times 58.55. It gives me 75.81 with 3 sig figs. That's going to be 75.8 grams of iron. Our next step is to compare that to what's given to us in the problem. We were given 167 grams of iron. Now we got to, use the brain and figure out what happens here. So this is saying when 35 grams of water react, I need 75.8 grams of iron. Do I have 75.8 grams of iron? Well, yeah, I have 167. So that's less than what's actually required. So that means I'm going to have excess iron, and water is my limiting reactant. That's how that works. Ooh, that's all right, great. Moving on. Part B. What mass of iron 3 oxide will be produced? So iron 3 oxide is a product. It's right here. What you do is you use what's limiting to calculate your product that's required. We did the same thing way up here in our bicycle. We used our limiting to figure out how many bikes we could actually make. So I can't use this value here, 167 grams of iron. I'll get an incorrect amount of product being produced. I have to use what is limiting. So I'm going to start with my 35 grams of water. And it's asking for a mass of iron 3 oxide. So my first one will be a grams to mole conversion. My next one is going to be a moles of water to moles Fe2O3 conversion. And finally, I'm going to convert my moles of Fe2O3 to grams of Fe2O3. Because that's what it's asking for, mass. I'm going to scoot this a little bit this way. Get room for my final answer, which should be grams of Fe2O3. So I've already done my work up here once. I could, duplicate it, make it a little bit smaller, throw it over here so everybody has that mass, and I'll have my 1 mole is 18.02 grams. For my balanced chemical equation, for my coefficients, for my heart of stoichiometry, that's going to come from my equation. So it looks like water happens to be a coefficient of 3, and iron oxide is a coefficient of 1. Pretty good. And then finally, I need the molar mass of my iron oxide itself. So iron oxide is 2 times Fe, and we're going to have 3 times O. You're going to have to do that out. It takes a little bit of time. We get 159.7 grams. So that means I have 1 mole is 159.7 grams of Fe2O3. Now, when I put this in my calculator, it's 35 divided by 18.02 divided by 3 times 159.7. I get the total grams being produced. So my total grams being produced here is 103 grams of Fe2O3. That's how we answer that question. So once again, I started with my limiting reactant with the amount that was given to me in the problem. Right, here it is. And I use that to predict how many grams of my product is left over. The last question says here, what is the mass of the excess reactant that remains after the reaction takes place? Oh, well, I can use this data right here to figure that out. because I've calculated previously how many grams of iron are required from my limiting reactant, I can use that to subtract for how many grams of iron are actually given. So I'll have my 167 grams of iron provided. I have my 75.8 grams of iron required from the reaction, right? Where is it? Right here. And I subtract the two. What that's going to give me is 91.2 grams of iron in excess. With sig figs, that's going to be 91 grams of iron in excess. If I did not do this calculation before, I would have to do that calculation starting with the limiting reactant to my other reactant to figure out how much excess would actually be required. But that's how that works. All right, we got one more calculation to learn today. That's called percent yield. Percent yield is a formula in your packet. And if you guys flip to the very back of your packet, you should find percent yield. Realize there's a difference between percent composition and percent yield. Percent yield, by definition, is actual over theoretical times 100. And that's going to give you basically how efficient your reaction really is. Theoretical yield, by definition, is the maximum amount of product that can be produced from a given amount of reaction. This is a calculated amount. That's from stoichiometry. All right, so this value right up here, 103, that's your theoretical yield. That's in a perfect world, that's how much product you could actually make. Your actual yield is what is actually obtained. You put it on a balance in lab and you get a correct amount or a corrected amount. It's always going to be less than the theoretical yield. All right, the theoretical yield will always be less than the actual yield. I wrote this backwards. Oops. The actual yield is always less than your theoretical yield. Good. I'm not going to start this video over, but realize that that's backwards, all right? So the theoretical yield will always be, we'll write more than the actual yield. Good fix. Now, to actually calculate this, you would be given, right, the actual yield. This would have to be given somehow. You know, I would have to give you a way to measure it or provide that information to you, and you're going to be calculating the theoretical yield using stoichiometry. So for your example problem, because this video is getting kind of long, we're going to use our previous problem, and let's say the actual yield is 92 grams. What is the percent yield? So the actual yield is 92.0 grams. Our theoretical yield, I believe, is 103 grams, right here. We divide those two, we multiply by 100. So, on your little calculator, you get 92 divided by 103. I'm literally doing this right now on my calculator. 92 divided by 103. I get 0.8932 times 100. I get 89.32% yield. Now, that's too many sig figs. Looks like I was given 3. I have 3 here. I was given 3 previously. So it's going to be 89.3% yield. That's a pretty good yield. All right. And chemistry is all about yields. The higher yield you have, the more money you're going to make, because the whole idea is to make more product. That is your lecture. That was kind of long. I'm glad we worked through it together. We'll be doing a lot of these problems. Don't fret.